Well, welcome back. Can you see the screen okay, or maybe we need one more light out here, I think. This one, thanks. Okay, so the project, of course, is due Friday. So I thought I'd first ask if there are any questions about that. No? Just chuckles. Could you please, let's see, please repeat. Let's see, snide laughter, is that one? So you might not get the factor of 2 I was hoping for in terms of performance improvement. You might, if you want, try it on a dense matrix, a dense matrix stored in sparse format, and see what happens there, because that'll be the upper limit, really, of performance. I mean, if you don't get speed up there, you won't get speed up on sparse matrices. So, but as long as you get, you should get some performance improvement. If you don't, then you're probably doing something wrong, at least on some matrices. You should also be careful to see that you're only reading and writing information, once. That you only need to read and write once. I mean, don't go through just because I say, oh, okay, don't read the integers. You have 2 columns, let's say, with the same non-zero pattern. Okay, of course you can't read this one, right? That's strictly out. But reading this one twice doesn't do much good, right? That's kind of pointless. So those sorts of things obviously are out of line. But if you read this integer pattern once and do all the work and as parsimoniously as you can. There may be some ways you've written the code that are inefficient, but as long as you make an effort not to read in data more than once and write it more than once than it's needed, that's the goal, to have you see at least algorithmically, if not efficiently in the code, at least algorithmically what can be done to improve the data flow of this. And of course, this kind of this may feel like you're doing something that's almost mechanical. I mean, it's almost may seem rather mundane, to be worrying about cache effect. But remember, cache is everything. I mean, you've got credit cards, you've got checks. No, sorry, I won't repeat that joke. But cache is it's physics. It's reflecting basic physics. So it is deeply theoretical. So the idea of minimizing data flow, data in and data out for an algorithm is vital. It's vital for the future as well, because we look at highly parallel algorithms, GPU-based algorithms. Moving data around is what's expensive. Everything else is free. Computation's free. It's moving data around. It's expensive. So it's a change. It's a big change. It's been coming for a long time, of course, but it's a big change in how people view algorithms. That it's the data flow that matters, not the operations on that data. Okay, so what I want to do today is look at Leftlooking Jaleski, and I want to go back also to the SIAM talk slides that I gave, because there's some nice color versions of this, which are kind of nice to go over. So I left off looking at this right here, and I derived this factorization, where we assume by induction that we've computed the first k-1 columns of L. And the question is, so the inductive algorithm would say this, well, if I can compute the first k-1 columns, can I compute the kth column? How would I do that? And then how would I compute the very first column? That's another story. I haven't written down the base case yet here. I'd have to do that. But it's a very straightforward one. It would just be, what would it be? I think it'd just be, this would be minus 0 here. There'd just be the square root, and then this would be just the division, A32 over the diagonal L22 for the base case. MATLAB fortunately handles that very nicely, because if k is equal to 1, this is an empty matrix, and MATLAB does the right thing with empty matrices. Empty times empty is, this is a 1 by 0. Think of when k is 1, this is a 1 by 0 matrix. What is that? Well, a 1 by 0 times a 0 by 1, this is LK, this is transpose, so it's 0 by 1, is a 1 by 1 matrix, also called a scalar. And it's 0 as well. So it does the right thing. You don't have to have a special case to check to see if k is equal to 1. So this is the MATLAB prototype of a left-looking Jaleski. And you know, we have one method for doing Jaleski. Why do we need another one? Well, it turns out that left-looking and right-looking are more amenable to implementation for cache-aware and GPU-aware and communication-aware type algorithms. They're more parsimonious in their data flow, or at least more regular, I should say, in their data flow. And so this is useful. But you see here, these two bullet items here just translate directly into these two MATLAB statements. So here's the square root of the scalar minus a dot product of two vectors, of a vector with itself. And then this piece right here is this L32. This is the kth column below the diagonal. And it's equal to the kth column of A below the diagonal minus, this is a matrix here. See, this is the L31. This is a whole region, a whole block of L and a whole block of rows and a block of columns times a row vector. And this row vector is the same one here as well. And then a division by a scalar. So that's left-looking Jaleski. And then let me show you this in a slightly different format. This is what I gave as an overview. So we're back now. We're now at the slide 68 out of 100 in the first talk, or if you remember the overview talk. So here's a colored version of this, colorized version of this sparse Jaleski left-looking algorithm. And what's important to see, and actually let me pull this other one back up, notes 4, is that this matrix multiplication here, okay, this in particular, this dot product, let's see. Okay, think about what's happening with this L12. There's a very definite structure to the sparsity of this computation. Look at this kth row of L. This is the L12 transpose vector. So what's happening here? So here's K. Yeah, you need to pay attention to this carefully because you'll be implementing this left-looking algorithm, I think. That's what I'm thinking about as the next project. Okay, so this is a matrix vector multiplication of this matrix here. This is the L31 matrix times this vector here, which sits right on top of it. Okay. Well, that's kind of handy because, and it's this times this transposed. Okay, so let's pull this apart and see what this is doing. So we have this L31 matrix, and we're taking this and we're transposing it and doing the matrix multiplication. So I've drawn it here and I've also drawn it there just to see what's going on. Now, you know what block matrix multiplication looks like. Let's ask now what happens when L12 transpose and L31 are multiplied. What does the structure of this computation look like? How would we compute this efficiently? Well, let's take L31 and slice it column-wise. That's convenient because we're going to store the matrix that way. And then let's look at this as a collection of scalars. And now some of these are going to be non-zero. The dots are non-zero and everything else is 0. So when you do this now as a block matrix multiply of this block matrix with this block matrix, what's happening is, suppose this is position 5, 7, and 11. Okay, so we have 3 non-zeros here, 5, 7, and 11 in the kth row. And how do we find that? Well, that's the E-reach. That's the reach. 5, 7, the set 5, 7, and 1, we know how to compute symbolically. That's the reach in the graph of L of the skeleton matrix, or just the entire matrix of A let's see, 1 colon k minus 1 comma k of the kth column above the diagonal. That's the result of the triangular solve. There's the Oliver twist coming back at us. The little guy who keeps coming, this triangular solve that keeps popping up. So this is where this pattern is coming from. It's the result of this search up the tree, the e-reach. It's the kth row subtree. And what's happening here when you do this multiplication, the column 1, if you will, gets multiplied by 0. So nothing, this doesn't take part. And so this 5 gets multiplied by the 5th column. The 7th scalar gets multiplied by the 7th and the 11th and so forth. So the only thing that takes part in the computation are those 3 columns. Or over here, if I were to draw it, it'd be just these 3 columns here. So that's the structure of the computation. And so all we have to do is find the reach to give us the kth row. And then in each of those columns, magically find the kth entry. Okay, how we're going to do that is another question. But let's suppose we could, in constant time, determine where is row k in column whatever. Oh, it's right here. Imagine we could find that in constant time. We can do that. That's not hard. It's a data structure trick. Okay, but in constant time, I can find these 3 values. Well, 1 value, 1 constant, unit time. And then suppose I store L column-wise in a conventional sparse matrix format, and suppose it's sorted as well with row indices in ascending order, then this data structure, this data that I'm trying to compute is very easy to obtain. If I can find out where this entry is, then the rest of the column is the stuff that has to take part in the multiplication. So this scalar has to be multiplied by the rest of its own column. And that's what's happening right here. One at a time. This is broken. This is a matrix and a vector, but broken up, it's a collection of vectors times a collection of scalars, each one adding to the final result one at a time, which can be done with gather, scatter. So I can have a single workspace that holds this kth column. I can scatter into it. I mean, you know how to do matrix vector multiply. This is easy. And then once I have the final result, then I can gather the result back into this column, and I'm done. So what we need to do then is so here's a MATLAB pseudocode. Well, it's not a pseudocode; it actually works. So what it's doing here is it's getting the kth column of A, extracting out of the matrix. I mean, this is not. I mean, MATLAB is not going to be a good language for expressing this efficiently, but it's a way of expressing it algorithmic at least. This is the matrix vector multiply. Okay, for every column in the kth row, every column J in the kth row, which is non-zero, which is a non-zero entry, that's, in other words, for J equals 5, 7, 11 for this example, this is what needs to be done. We need to take this vector and subtract from it that scalar at the top of the column times all the vector below that scalar, and subtract it from the workspace. And then that workspace, that updated vector, gives us 2 things. The diagonal is the LKK entry, and the thing below the diagonal, it needs to have the division done to it, which is not that matrix. It's not the matrix vector multiply. It's the second equation. So this is a prototype. But let me now show you a color version of this data flow here, a little slightly more pseudocode version. So there's the left-looking Jaleski algorithm. Has to it has to find the non-zero pattern of the kth row. This is the MATLAB find, if you will. Of course, MATLAB is not going to implement the e-reach algorithm at that point, but we could do that. We can determine which columns have non-zeros of interest. Do the matrix multiplication across those columns, and then gather the result into the kth column. And this is what the data flow looks like. We find those 3 entries here, we grab them, multiply them by the things below, and add them to this column. So I haven't, and then do the division. Now I haven't yet showed you how we find these. Suppose we know, okay, 5, 7, 11. We can find that very easily. Because we don't have to traverse the matrix L to determine the number 5, 7, 11. That those are the columns that have non-zeros in the kth row. Because we can just start with the entries in A, in this column, and then walk up the tree. So presumably K would be here, and suppose, let me just make this some tree. Suppose it looks like that. Okay, suppose entries 5 and 7 are non-zeros in the A matrix here, and as you walk up the tree, you'll also find, oh, 11 is non-zero as well, and then you hit the top of the kth row subtree, which is always K. So we traverse the paths and we find those 3 entries. So that's very easy to do symbolically in time proportional to the number of entries in the result. So it's asymptotically optimal. The total time to do all the E reaches across the entire algorithm will be order L, because every time we see one entry, it takes a unit time to touch that entry. And every entry is seen once right here. Okay, now this is the idea here that each of these 3 dots here, each of these entries is seen just once in this entire computation. That is what's used to find them quickly in constant time. Because think about now what's happening in this computation. Suppose, and so this is going to be another inductive type algorithm here. Suppose I'm at the kth step of factorization. Okay. And suppose I have an index, a pointer, for every column that I'm allowed to advance. And let's suppose that magically each of those 3 pointers already point just to the right place. Okay, so if I look at pointer 5 and pointer 7 and pointer 11, then so if I look up the pointer for the 5th column, it'll point magically to the kth entry of interest. Now how I get here, of course, is another story. P7 points magically to here, P11 points magically to there. Now, if we have that on input at the kth iteration, I have to make that true for the next iteration. The next iteration, all the pointers must point to entries that are numbered K plus 1 and below. Well, to get to that fact, all I have to do is advance just these 3 pointers. There's 3 other non-zeros down here in various positions. Advance each 3 of them by 1. Increment each of these 3 by 1, and they now point to the next place. So the next time you ask the question, oh, look, suppose this K is equal to 12, and here K is equal to 27. So you're in column 7, and you find the pointer pointing to the 12th entry in the 12th row. And you use it. You do the computation, you update, this is the 12th column of L. And then, the very next thing that happens is then, for the 12th step, you increment this pointer. Now, this pointer is pointing here to the 27th row, which you don't care about for computing the 12th row. And you compute the 13th column of L, the 14th, the 15th, the 16th, and so forth. You come to the 27th step of the algorithm, and you're computing the 27th column of L, and you find, oh, look, row 27 has column 7 in it. And I know right where it is. So these pointers start out to point to the diagonal entry. They can all be initialized to the diagonal, and then one past the diagonal. Okay, so they all start out pointing 1 past the diagonal, because it's the first thing you're going to find, because you don't need the pointer to find this diagonal entry right there. But the first off diagonal entry, suppose it's, say, 15 for this one, okay? That's going to be the very first entry that participates in this computation of multiplying this scalar times the rest of the column, adding it to column 15. That'll happen when you're at k equals 15. Okay, so these pointers that are going to advance through the matrix, column by each one in their own column, is going to start out with 1 plus the diagonal right here. And think of this as a queue. Every time you operate on this entry, multiply this scalar times the rest of it, then this is consumed, and we just increment this pointer by 1. For the next computation, we increment it then to the next non-zero. So the next thing that's going to happen, suppose it's 27. The next thing that's going to happen in this column is that entry 20 in row 27 is going to be multiplied by the rest of the column and added to here. And that'll happen precisely at when k is 27. So all we need to have then is a way of determining the kth row pattern of the matrix. Once we find that, we can go to those column pointers immediately and say, hey, P5 and P7 and P11 all point, we could do an assertion here, that the row index, if I were to look up Li of P of 5, I can assert that that will be K. If 5 is in the reach for the kth row. So for any column index j in the reach of the kth row, this will be true. I'll know I have that entry exactly. And then when I extract that entry, all I have to do is do pj plus plus, move ahead, and we're done. Now, before the notion of the elimination tree was introduced, this algorithm was implemented in a slightly different way. Not very different way. Then really all you need this elimination tree and the kth row subtree and all those theorems for finding, all that's used for is to find this reach. So if there's another way to find the reach, then that'll suffice. And the other way that was used before the notion of the elimination tree was just a collection of queues implemented with linked lists. And the idea here is that you have your matrix, and you've already done the symbolic analysis, so you know the non-zero pattern completely. And you have this first off-diagonal entry, which of course is the parent of the elimination tree, but that was not observed at the time. So there's your matrix below the diagonal. And so what happens is we have a bunch of linked lists. We have n of them from 1 to n. And in the kth linked list is a linked list 5, 7, 11, and then terminal. The sum total, this is a trick that's often used in these algorithms. I can create n linked lists, each with holding up to n entries each in a total space of n. Because any given node, say, or entry 5 or 7 or 11, will appear only in one of these lists. I think I described this algorithm before, didn't I? I just have two arrays, a head and a next pointer. This is a head pointer. Head 1 through n is the head of k is the head of the kth list. And then next of 5 would be equal to 7. So these aren't pointers, these are indices. So they're much more efficient to traverse. I can find where is node 5. I can immediately know where it is. So this is, if you will, gives the inverse of these pointers. This says, given k, what are all the set of j's? So given k, what are the set of all these j's such that we're pointing to the right place? And that's the answer here. This is the set. And then once this set is processed, you take 5. So here's column 5. Now, you're not going to implement this algorithm. This is not necessary. You have the E-tree reach algorithm, which is much simpler. Well, much more theoretically appealing anyway. And It is actually better because this one requires more data movement with all these pointers, indices. So if I'm at column 5 and I see here k, suppose k is 12, then this guy, this node 5, once I've processed this kth step of the algorithm, the 5 gets removed from here, and this whole list gets emptied. And 5, suppose, what did I say the next thing was? 27. All that'll happen is, in the linked list 27, we'll insert 5. So the next time I come down to, so I'll come down this algorithm every time extracting entries out of the kth list, grabbing things out and putting them down farther. Then when I come to 27, I'll see 5 again. And this assertion will be true here. Because I will have also incremented the pointer for 5 to the next entry. Oh, 15, I'm sorry. Well, whatever. I guess 7. I guess my examples were off here. This should be 15. If I'm looking at column 5. To stick with the same numbers. Well, or better yet, let me change this to 7 instead. Sorry about that. Getting my numbers mixed up. There. So column 7 then is the one I said was, the next entry was in row 27. So this is how this left-looking Jaleski was implemented from the very beginning. The very first sparse Jaleski algorithm that was asymptotically efficient. I mean, there had been sparse Jaleski codes, I think, before this that used all kinds of different, there's skyline methods that store, they don't try to exploit all the zeros, they just store entries in a skyline form. A skyline form looks very different than what you've seen here. I haven't talked about them because they're not really used anymore. But a skyline form, what happens is you imagine your matrix looks like this. And all of this is 0, which you only exploit the sparsity above the topmost entry in every column. And everything down here you store explicitly. Every 0 in there is stored. So it's like a variable band structure. It just moves up and down. And with this, you don't have to exploit a lot of theory to do the computation on this algorithm, or on this data structure. It's a much more simpler, theoretically it's simpler, but it's asymptotically completely inefficient. This is asymptotically efficient. It doesn't necessarily need to use the elimination tree to get you there. But once you know about the elimination tree, finding these facts is a lot simpler and more elegant and faster. So that's left-looking Jaleski. And now let's look at what we can do better. So this is like your project on doing this. Really what you're doing is a supernodal on-the-fly solve. Okay, you're looking at columns and saying, oh, look, they have the same non-zero pattern. You're extracting this out of your matrix. Okay, what if I did the Jaleski factorization like this to begin with? Okay, what if a collection of columns all had the same non-zero pattern? The elimination tree structure would look like this, and the non-zero pattern of this column would look like that. Now what I can do is I can change the blocking. Okay, and what I can, this block matrix algorithm, which I showed on the other slide, this 3x3 block right here. Okay, there's nothing in this algorithm that actually requires L22 to be a scalar. There's nothing here that requires L22 to be a scalar. Well, except I've written a square root. Okay. If L22 is not a scalar, what could we do? I have these two expressions written out, but I don't have to write them out this way. Let me pretend now that L22 is, say, a small matrix, however big it wants to be. 2 by 2, 10 by 10, 30 by 30, whatever. It's a matrix. It's not a scalar. Okay, so we have these two equations. And let me see if I just have the two equations flat. No, I don't. Okay. I'll have to just rederive them. So we have that L, and I'm going to write capital L's for all of them because now they're all matrices. L12 transpose times L12 plus L22 L22. And I'm not going to write it squared because it's no longer a scalar, equals A22. So that's, I'm still assuming that I've computed the first block of this matrix. So I've computed all of these, and now I want to compute this. But now I'm assuming that L22 is a block, not a scalar. So L32 is a matrix, and this is a L22 then would be a square matrix. And again, then each of these would be matrices. Not that A22 would not be a scalar, but a matrix. So I've written the one equation, and then the other equation will be this column times this row. So it's L31 times L12, L31, L12, plus L32, L22 equals A32. Okay. So that's what those are the two equations. So, and let me now circle the terms that I know. So I know A22, I know A32. I don't know L22, nor this L22. I don't know that yet. And I don't know L32 either. But I do know all of this. Oh, I said I'd circle the ones. What did I say? Oh, I'm circling the wrong ones. I'm circling everything. That doesn't help. Okay, I'll circle the terms that I know, and I'll leave the other ones. So these I know, and these I know. The question is, can I solve? These are two matrix equations now, and vectors and such. L22 is a matrix. Can I solve for L22 and L32? Yeah. Okay, look what happens. Actually, this is, I'm sorry, I made a mistake. Minor mistake. If this is a scalar, I have to actually write this as L22 transpose, because if I take this matrix and transpose it, this is actually the transpose of that matrix. When it was a scalar, I didn't have to worry about it. Well, unless I worry about complex matrices, then if X is a scalar, X transpose is the complex conjugate. So I need a little t there to be more careful. And then for this one, do I need a transpose there too? Let's see. Yes, I do. I need a transpose here. Okay, there. Now I've got two matrix equations that I would like to solve. Well, yes, I can look at this one. L22, L22 transpose equals A22 minus L12 transpose L12. These I know, and L22 I don't. Well, that's just a little mini Jaleski factorization of a small little block. And it's a dense matrix, no less. It's a dense matrix because the supernode looks like that. And so in this case, it's a little 3x3 dense matrix. Okay. I have to factorize a 3x3 dense matrix. How do we do that? We use a different method. We use a dense Jaleski factorization method on that little 3x3 block to compute L22. Not exploiting sparsity at all. Do that? That's a different algorithm. That's straightforward. We can just write it. It's a different problem. Okay, no sparsity exploitation needs to be done at all. It's a dense matrix. So now we have L22. Now let's look at this one. Now all I need to do is compute L32. Well, then I can write L32 L22 transpose equals A32 minus L31 L12. And now the question is, how can I solve this for L32? Well, it's a triangular solve. And it's perhaps better seen if I transpose both sides of the equation. I get the following. L22 times L32 transpose equals all this transposed. So what that looks like is a little dense matrix, L22, times a right-hand side X equals a right-hand side B. But what is X? X is L32 transpose. It's a dense matrix. Here it's a 3 by 3 dense matrix. In general, it would be 3 by whatever, however many non-zeros there are. So it wouldn't have to be square as it is there. This is my supernode below the diagonal. This is the diagonal entry of the supernode. The diagonal entry, the diagonal matrix. This little lower triangular part here. And the rest of it is the supernode I'm trying to compute. So once I do the solve, I'll have my supernode. I'll have those blocks of columns of L right there. And the right-hand side is itself then can be stored as another dense matrix, because I can take, let's see if I have this picture. So I have to do, and this is the other interesting computation that has to be done. So I have several matrix multiplications to do. And the way I did it before was I looked at column by column and took a scalar and clumped them together. It gets a little more interesting in the matrix case. Let's see. I think I'll stick with this. So what has to happen to compute this matrix, these 3 dots now, okay. This dot is now a matrix, not a scalar. I have to take this matrix, multiply by the matrix below it, which is an operation within the supernode itself, a child supernode here, or a descendant. It's a matrix multiplication, and everything is nice and beautifully regular inside there. I have to take that work and then add it into this matrix here. And it's a subset, so there could be zeros here for which is non-zeros here. So there has to be a matrix multiplication within this matrix times the one below it to get a dense matrix result. And then it needs to be unfolded a little bit and put into this supernode and spread apart a little bit, because there could be whole zero rows here which appear here but do not appear here. So that has to be done for every supernode descendant that has any contributions to this column. So what's happening, if you look at the tree, the tree has been globbed together. Groups of supernodes have been globbed together into a supernodal tree now. It's a coarsened tree. And then the kth row subtree now has also been sort of conglomerated together into larger chunks, larger nodes, which are individual nodes in the kth row subtree. And I've got to take all of my descendants then in that kth row subtree and take all of their computations like this and add them into the root. So that's what the data flow looks like. You're going down deeper into the tree, doing some work across every node of this conglomerated or supernodal kth row subtree, and then adding that work into the kth supernode. So that's a block matrix multiplication. Every piece of that for every child or descendant supernode is a dense matrix operation. And so cache just loves it. It just eats it up. You bring in two dense matrices, the supernode, you multiply them together, and then you put them out into the resulting output supernode, the kth supernode. You add. And then there's also a very nice method for exploiting cache inside the dense Jaleski. Right? We can get very high performance there. And then this is a dense lower triangular solve. This picture right here, okay, can completely ignore sparsity. If I store my supernode such that this is stored as a dense matrix, which in your case you're not doing that for this project, but it could have been stored as a conventional dense matrix, then I've got a dense lower triangular solve and a dense matrix and the dense matrix here. It's just a dense, it's an operation which can be made very fast, and people have worked very long and hard at dense matrix operational kernels, libraries of matrix operators, which do this sort of thing very quickly. So we can leverage that performance. They do these things very quickly because they can exploit the hierarchy of the memory better, and they're physics-aware algorithms, if you will. Okay, theoretically aware of the fundamental theoretical limitations of physics, which is to say they exploit cache. Memory hierarchy in particular. So that gives us the sparse Jaleski and the supernodal sparse Jaleski as well, and the supernodal. So I already explained. Let's see. This is a MATLAB implementation of that algorithm, which is kind of handy to see. So I only drew the picture. But here what's happening now, we have the MATLAB looks just the same. This is because MATLAB works great on matrices or scalars or vectors just without even knowing. I mean, the syntax is really elegant. What this algorithm starts out assuming is that you have a partition of your matrix into the supernodes. So S is a vector of S of T is the number of columns in the teeth. That sounds funny. The teeth supernode. It's a very sharp algorithm here. There's a real bite to it. So we have, so the cumulative sum of S will be N. So it just defines where the supernodal boundaries are. So we just need to work across those supernodes. This is J, the jth supernode. I guess I should have used K. Well, I didn't want to use K because I'm using K down here. We need to find the start of the jth supernode and the end of the jth supernode. And now we want to work on all of those columns at a chunk. So rather than doing the square root now, a square root is just a one-by-one Jaleski factorization, right? Think about it. If I've got a matrix LL transpose equals A, and L is a scalar, it's just L squared equals A. Solve for L. L is the square root of A. So a square root is a one-by-one dense Jaleski factorization. And in fact, in the algorithm, if you have even if you have a supernode that's just a single column, we still call the dense Jaleski, and we end up doing a square root. Kind of boring, but it works, right? I don't think I have a special case. Well, actually, I should look at the code again. I don't remember. Maybe I did put a special case for the case where I have a supernode of one column, but I don't think I do because it's just not worth it. So there's this matrix multiplication here that has, this is the kth block row. It has to be multiplied by itself. That's that stripe. That's this piece right here. Okay, that piece has to be multiplied by itself, and the result put here. And then these pieces also have to multiply by the piece below it, where each of these pieces now, each piece here is a whole matrix, and this is a whole matrix. So that's what's done here. It's just done all at once rather than piece by piece. And then MATLAB, the division operator, works great for matrices as well. This is now slash the matrix operator, not divide the scalar operator, by LKK transpose. So this is doing this transposed lower triangular solve right here. So if this is my problem here, I could solve this by writing it this way in MATLAB notation. And that does the triangular solve for me right here. So this is A32 minus L, is it 31? Yeah. Minus L31 times L12 transpose. There's the transpose. Triangular solve with the LKK block matrix. Because, see, this is not just one column. It's a whole chunk of columns. This algorithm, of course, is not, I mean, it's just it's a working MATLAB prototype. You wouldn't, unfortunately, be able to write the code this way to get efficiency out of it because MATLAB does not really know what you're doing. It's too general purpose at this point. And doesn't even attempt to describe how to exploit the sparsity of all this computation. There's no way that the MATLAB can somehow magically come up with all the theorems to show how do you efficiently do this multiplication as a collection of dense matrix products. It can't figure that out. And in fact, in this algorithm, it's just a dense matrix. All right. I'm not even trying to even pretend to exploit sparsity here. Okay, so that is supernodal factorization. So that's the that's supernodal. Now I want to talk about multifrontal, which I don't have slides on this page, unfortunately. Let's see. No, I didn't create slides, so let me go to this one instead. And let's look at a different way of factoring a matrix altogether. And I've got 4 minutes left, so I'm only going to give this a very short view, just with one picture. In fact, this says LU factorization, but we're going to pretend it's Jaleski because the pattern of the matrix is symmetric. Okay, there's yet a different way there's many ways of factoring a matrix, of doing a dense Jaleski factorization. We can instead do a outer product method. So if you take the matrix L11, if you block the matrix this way, this is L12, we'll call it L21. This is L21 transpose. This is L22 transpose. If you block the matrix this way, where this is a scalar, and this is a whole matrix of size n-1 by n-1, okay, then you end up getting, and then you ask the question, how do I do Jaleski factorization this way? You end up with the factorization looks like this. Let's see, L11 transpose equals A11. Well, that's a square root. That's easy. Then we get L11 transpose equals A21. Well, if I know L11, I can get L21 just by doing a scalar division. Divide this vector by this scalar. So that's easy. That's easy. And now I have L21 times L21 transpose plus L22 transpose equals A22. And that is a Jaleski factorization by induction. So we have L22 transpose of a modified matrix, A22 minus L21 transpose. So what we have to do, if we want to write an algorithm that follows this form of the computation, we need to be able to take a square root of a scalar. That's easy. We need to be able to divide a vector by a scalar. That's easy. And we need to then repeat the continue the Jaleski factorization on a modified matrix. This is the hard part. How do you represent this? Imagine you want to store A22 as a sparse matrix. What do you have to do? You have to subtract out this matrix, this vector product. And what is that vector product? It's a clique in the graph. This is L21. And L21 transpose looks like this, the same pattern. When I multiply those two together, I get a little 3 by 3 set of entries, 9 entries, which is maybe I'll add a fourth one here just for fun. So 4 by 4. What that represents is a clique in the graph. So I have to take these 16 entries and subtract them from the graph of A. And if there's no numerical cancellation, what's happening is I'm taking these 16 entries and adding them to the pattern of A22. These 16 entries represent all pairwise connectivity of all of these 4 nodes. These are 4 nodes in the graph. All of those 4 nodes are now connected to themselves as a clique. This is a clique in the graph. So it's like you're taking the sparsity pattern of a matrix here, and you're saying, here's a clique, and then here's the next clique, and here's another clique, and here's another clique. And now how do you represent the summation of this? Well, you don't need to sum them all up right away. You can say, here's my original matrix, and there's a clique I need to add to it, there's another clique, and there's another clique, and another clique, and another clique. There, I've got this pool of cliques. And all I need to really have to do then is this computation here at the kth step. So at the kth step, I need to be able to get out now these modified pieces of the matrix to say, well, here I need to collapse the cliques together, okay, and then do this division. So that's the multifrontal method, where these cliques are stored separately, and then they're only brought together when they're needed. So I'll elaborate on this picture here where this comes from. But each of these pictures here is the clique, and the arrows represent when they can be folded together to do and operate on those pieces. So I'm coming to the end of my time, and we will pick up here then on Friday. Thank you.